So we are talking about rotation by a large angle. I mean, can be a fairly large angle. So we call it a finite rotation. Change in a vector. So we are looking at change in a vector. And see, if I want to describe the change in any vector, it's better if I describe the change in a radius vector, because any vector can be written in terms of this subtraction of two radius vectors. So I do change in a radius vector. That will suffice for any vector. By an angle, say phi, capital Phi, say, just what we have been using, while about an axis. The axis can be given by an unit vector, so it's about an axis n cap. Okay, there is a little bit of mathematical inconsistency in that statement, that an axis can be given as n cap. Minus n cap will also suffice, and then you have to choose amongst the minus and the plus. But let's not go into that much detail for the time being. Okay, so what we are looking at, so you have an axis. So let me draw the axis with this color. This is my axis. And I have an origin in my axis, which is this point. Now I draw a vector . This is my vector. I call this vector the vector R. So this is the original orientation of the vector essentially. And then this vector changes. Now this thing rotates around the axis, and the axis, let me call this the unit vector along this direction that we have already decided that it's n cap. So R rotates around n cap, or this tip of the vector rotates around n cap, so we call this point P. So it will trace, as if it rotates, it will trace a circle like this about this origin, which I call N. Okay. And at a later time, the vector comes at a different position, and that position is this. So this is the new vector, which I call R prime. Okay. And then I draw this line. This point I call Q, and I draw this line. Okay. So I have Q. The same picture I draw here, looking from the top. By the way, this is the angle of rotation, and that we said that this angle of rotation we will call capital Phi. So I draw the same picture from the top. So it will look like a circle. The center of the circle is N. This is that line NP, and this is the line NQ. So this is my P, this is my Q. I draw a perpendicular on this line. and I call this position V. So this is perpendicular, I call this position V. This, if you remember, is phi, this angle, and imagine that this point is S. Okay. So this is the geometry. So if you wish, I can draw that V also here, but it's in a projection kind of thing. This is the top view. The right hand side is the top view. So this is the top view. These things are often called perspective view. Or let's say side view. These are called perspective view to be more technical. So let us call this side view. So let's see few things here. First, you realize that modulus of vector r is same as modulus of vector r prime, which we know that is supposed to be because of rotation. So np, which is the vector r, modulus is. So I'm writing the vectors this way. I'm not, okay. Nq. So that's also true, right? See, np is not vector r, but np is this distance and nq is this distance. They're all same, so as ns. So their magnitudes are all same. And the origin I should call O. Now, what is On, this vector? Well, it has a direction n cap, and the magnitude is whatever you will get by projecting r into n, because this is a plane which is perpendicular to the, this plane is perpendicular to the axis. So which means that On is r projected along n, which is r dot n cap times n. You'll agree that the vector np is then the vector OP minus the vector ON. Vector OP is nothing but R, and ON we have just calculated. Okay. What is the direction NS? The direction of NS, which I can write this way, that's the unit vector along NS. That is, you see, it's n cross r. So n is this direction along the axis, and r is the direction which is going that way. So if I take the cross product of these two, then I will get ns, which is perpendicular to both r and n. So this direction is along r cross n. So I can write this as this way. Now, before going further, let us check what is the modulus of r cross n. So r cross n cap modulus, or it is easier to calculate the square of that. That is nothing but r cross n cap dot r cross n cap. Okay. Now, here I want to teach you a little bit of vector analysis, because this becomes easier to calculate this way. If I have A cross B, if I take the ith component of A cross B, this can be written as something called epsilon ijk. It's called evasivator symbol. Jth component of B A and kth component of B can be written this way. Okay, what is epsilon ijk? Well, epsilon ijk equals 1 if I comes before j and j comes before k. Okay, this is equals -1 if not satisfied. Which essentially means that instead of writing 1, so epsilon 1 to 3 will be 1. You should not say I comes j before k, etc. So I should say 1 to 3 here. So epsilon 1 to 3 is 1, so is 3 1 2, or so is 2 3 1. But if I instead write epsilon 1 3 2, which is the other way, then it will be -1. And this is 0 if any index repeated. This is just a very closed form, very nice closed form of writing the cross product, and we'll see that it makes calculating this a lot easier. You can try to do it with the the vector multiplication rules, and let me show you that how I will do it right now using this. Okay. So what this becomes, so this I will put in box, and this is out of the calculation. So r cross n here is then epsilon ijk rk, rj nk. So that is the ith component of r cross n cap. When I take a dot product, obviously I multiply the ith component with the ith component, and remember that all the indices which are repeated are summed over. So this I can write ILM RL NM. Okay. So now this is epsilon ijk epsilon ILM and then RJNK RL NM. Now epsilon has certain properties, and this you can prove just by checking the combinations. So if I have epsilon I jk epsilon ILM, this is the following. So here the thing is that one of the index, the first index is common, the second and the third indices are different. So this comes out to be a Kronecker delta. First I have j with L, so second here and second here, times second here and third here and third here. This minus, now I take the second from the first and the third index from the second epsilon, and then the rest. Okay, it's very easy to remember. Second, second, third, third, second, third, third, second. Okay, and let's put that back here. RJ, RL, NK, NM. Okay, so let's see what do I get for the first term. So for the first term, I have delta JL, which means if J is not equals to L, this term is 0. So I have Rj here, RL here. So J has to be L, which means this is RL times RL, which is nothing but R dot R. And then I have to have k equals to m, and k equals to m means n dot n. N is a unit vector, n dot n is 1. So I don't need to write that down. Minus, now delta jm. So rj and then nm. So this is then j has to be equals to m, which means rm nm. So this is just r dot n cap. And if you look at kl, so again that is r dot n cap. So this is square of this. So this is what I have as r cross n cap squared. Okay, let us calculate. So this is r cross n cap sitting over here. Square of that is we have calculated. Let us calculate square of np, which is r minus r dot n cap times n cap. So r minus r dot n cap times n cap. This entire thing with its own dot product. So what do I get? First term is r dot r. Second and third term is same. So it's 2 r dot n cap and then r dot n cap. So square of that. And the third term is n cap dot n cap is obviously 1. So this is again r dot n cap square. So this is essentially r dot r minus r dot n cap square. So we realize that this is exactly same as that, which means, you see, NP is this. NP has the same magnitude as NS. NS has the direction of r cross n cap and the magnitude of NP. So I can write NS as r cross n cap. Right? So NS becomes r cross n cap. The vector NQ, I can write as a combination NV, which is the projection of NQ along NP plus NS, NV plus VQ, and this angle is phi. So NV can be written as NP cos phi and VQ can be written as NS sin phi. So NV is cos phi and VQ is NS sin phi. Just decomposed it into the two perpendicular components. right? So that's simple geometry. This is top view. Let me keep it here. Okay, so now let us try to write down. Let us try to write down r prime in terms of r. So what is r prime? The r prime is OQ, the vector OQ, which is nothing but vector ON plus the vector NQ. And NQ I have just written here. So let me now substitute. So I will write ON plus NP cos phi plus NS sin phi. Okay, so let us do it here. So r prime is ON plus NP cos phi plus NS sin phi. ON was the vector r dot n cap times n cap. So that is when over here NP is r minus r dot n cap times n cap and NS is r cross n cap plus r minus r dot n cap times n cap, and then I have cos phi plus NS is r cross n cap sin phi. Please check if r cross n cap gives you the right direction or it should be n cap cross r. That's your homework to check. Okay. Now I will rearrange this a little bit. So I have r cos phi here, which I write first. And then I take n cap r dot n cap common. And what I get here is 1 minus cos phi and then I think this should be n cap cross r. So let me correct that here. Please check. Okay, please check. It should be this. So that whether r dot n cap or n cap cross r depends on whether you take right hand system rotation or left hand system. This should be the correct choice for the right hand system. But you also please check. Okay. So this is how a vector r changes in a finite rotation, and you see it's fairly complicated. If I write in terms of the Euler's sense, in the Euler's theorem sense, that in terms of the direction of the rotation n cap and the angle of rotation phi. Okay. If I consider a finite rotation though, this becomes a little simpler. So if I consider finite rotation, so which means that, or infinitesimal rotation, sorry, not finite rotation, but infinitesimal rotation. So I take, for phi, I take d phi, which stands for infinitesimal rotation. This implies that for all my cos phi, I can replace it by 1, and for all my sin phi, I can replace it by delta phi or d phi. So then r prime cos phi is 1, so this is just r. Here cos phi is 1, so 1 minus cos phi is 0, so that term doesn't exist. So plus I get n cap cross r d phi. This is very interesting because now I can write the change in r as dr, which is r prime minus r, as n cap cross r times d phi. I can define now, I just define a vector d omega, which is n d phi. So this is infinitesimal rotation vector. Then dr becomes minus r cross d omega. This is one way of writing it, or even I can write dr cross dr by d phi as minus r cross n cap. Now these will be useful for us shortly. Okay, now, so we are talking about infinitesimal rotation here. So let me show you a few things that is good about infinitesimal rotation compared to the finite rotations. So remember what happens in a finite rotation, so a successive finite rotations. You see, we have already done one thing here which is interesting, that we have defined a vector d omega which represents a rotation, an infinitesimal rotation. It's a vector. Okay. Previously, when we talk about rotation, we had a matrix which is not a vector. It still have three components, three parameters which specifies the matrix completely, but it could not be written in terms of a vector. Here I can write it in terms of a vector, the infinitesimal rotation. And why is that so? So that is what we will try to understand now. So for that we look at successive finite rotations. So say I start from r, I go to r prime, and then I go to r double prime. And to do this, so from r to r prime I have 1 phi, say phi 1, and here I have phi 2. So these are two rotations. Obviously you have n1 cap, n2 cap, right? So this is what is giving the rotation. Now these two combined, I am claiming that I cannot write them as a vector. Okay. Let us say that we can. So then we will try to prove that that doesn't work. So if we can write this as a vector, if as a vector, just like we did for d omega, So if I write this as omega, and so again I'm putting a question mark here and this highlighting this if, and this I write omega 2. Okay. Then Euler's theorem tells you that if I go from r to r double prime, there must be a omega 3. And this omega 3 has to be related to omega 1 and omega 2 this way, because these two rotations gives rise to the third one. Okay, so fine. So I get, using Euler's theorem, that omega 1 plus omega 2 equals omega 3. There is no problem in that. Now I say that, okay, what I do now is I start from r, I use omega 2 first, and I go to some r, say r1 prime. It may not be the same r there because I'm giving it a different rotation. But then if I give another rotation, omega 1, which is omega 1, I must land to r double prime, because Euler's theorem tells you that omega 3 must be equals to omega 2 plus omega 1. The single rotation should bring from there to there, and that single rotation should be the combination of the two rotations. So I should be able to write them down this way, because they are vectors, so I should be able to add them. They are vectors. But we know that these two are not same. We know that rotations do not commute. This we have seen. So this doesn't work. Which means, no, we cannot represent finite rotation by a vector. That's why we used a more complex thing called a matrix to represent the finite rotation. But here we see that for an infinitesimal rotation, we have already defined an infinitesimal rotation vector. How do I do that? How can I do that? So let's ask that question. So for infinitesimal rotation, what we claim is the following. We claim that, say I have any component xi, so this is now infinitesimal rotation. So I have a vector, and the components of the vector I call xi. By rotation it changes to xi prime, and it is related to xi. There is a very little change in xi, so that's why it's infinitesimal, and can be written this way, where these are 9 very small quantities. Very small numbers. Or you can write this as, so this if I write in now vector and matrix notation. Okay, so before that let me write this just as a component itself once more, because this xi I can write this in the following way. Delta ij times xj is xi, because delta ij is 0 if I is not equals to j, so it's a Kronecker delta. So I can write it this way, and now you see that so if I go, so this have the form as aij xj. So this has the exact same form as the rotations that we have seen with the matrix A. So this has the form as x prime as ax. This A is again not a vector, obviously. It's the rotation matrix, the orthogonal rotation matrix that we have been talking about so far. But in this case, for infinite rotations, for infinitesimal rotations, for infinite and infinitesimals are far away, your A is nothing but, it's almost an identity matrix plus some little epsilon, right? So let us see what happens in for successive rotations. Successive rotations will now mean that I will have epsilon 1, and then I have to multiply this by the first. So this is the first rotation, this is the second rotation. Now if I do that, I get I bar, I get epsilon 1 bar, epsilon 2 bar, and then I get epsilon 1, epsilon 2. But this can be set to 0 because epsilons are very small. So we ignore all terms which are above linear in epsilon. And now you can see that if I would have done the other way, if I would have done it this way, so epsilon 1 first and then epsilon 2, two rotations, this would have been the same. The matrix multiplications, sorry, matrix additions are commutative, so these two are same. So for finite rotation, it doesn't matter which way you do the rotation. So for finite rotations, order of rotations doesn't matter. Think about it a little bit more, because not a little bit more, a lot more, because you can have many infinitesimal rotations to give rise to a finite rotation. So where does the fact the commutativity is lost as you go from infinitesimal rotations to the final rotation? Now, so let's talk about the Euler matrix. A, and so which was parameterized as phi, theta, and psi. So remember, this was z, x, z sense of rotations. If I consider the infinitesimal case, then we write for phi d phi, for theta d theta, and for psi d psi. So then A, or should I write dA, it's also a matrix, will have this form: d phi plus d psi 0 minus d phi plus d psi 1, d theta 0 minus d theta 1. Okay, you can verify that. You have to just put phi as d phi, theta as d theta, and psi as d psi, and remember that all cos of small equals 1 and sine of small equals that small itself. So if you use this, you will get it this way, which you see is clearly an identity matrix, the 1 1 1, everything else 0, plus a matrix which is 0 d phi plus psi, 0 minus d phi plus psi, 0 d theta, 0 d theta, 0. And this has the form as I plus epsilon. So this is your epsilon matrix, which is giving rise to the finite rotation that we are talking about. And you can check, so we wrote this d omega over here, we define this d omega over here. You can check that d omega will come out to be d theta x cap plus d of phi plus psi z cap. It's easy to check. How do you check? What all you do is you calculate, okay, so you calculate r prime in terms of r, in this way. Okay, so what you do is you calculate the x components, x prime, so that will come out to be, this is x from here, and then you will get d of phi plus psi y times d of phi plus psi. Okay, so you can check that you will get that from, if I use this d omega, if I use this d omega here, I will get this, and then we calculate x prime from using dA, so that is what we wrote down here. You will get the exact same thing. Okay. So epsilon matrix is this. So which also tells you that for this d omega, if I write it in terms of three components, omega 1 x cap, omega 2 plus omega 2 y cap plus omega 3 z cap, then omega 1 is d theta and omega 2 is this is z cap, omega 2 is 0, and omega 3 is d of phi plus psi. Okay, so I can write epsilon also in this way. Omega 3 was d of phi plus psi here, so then 0. Here you see that I have minus d of phi plus psi, so this is minus d omega 3, this is 0. This place I have d theta, which is omega 2, omega 1, so I have d omega 1, and this place I have 0, this place, this should be minus d theta, and then 0, 0, minus d theta is, these are the infinite rotations, right? So I should write with the d. So clearly this is an antisymmetric matrix. In fact, this is the same matrix that we had seen here, or this is the same thing that we have seen here, right? This is the same equation, dr equals n cap cross r d phi. And there we wrote down dr by d phi, we wrote this down, we wrote down dr by d phi as minus r cross n cap so this also I can write minus some n, some matrix n transpose of that times r. Okay, and you can check this n matrix. So I'm going a little fast here, but it is just because it is not very difficult to check. This is an antisymmetric matrix of this. So what all you have to do to check is that put it there. So transpose of this actually. No, it's all right. The transpose I've taken already there. So what you have to do is that you have to just put the transpose of this here, which will just change the minus signs to the plus sign and the plus signs to the minus sign, and calculate dr d phi. You will get the exact same thing. So dr d phi, remember that dr is the change in r, so it's r prime minus r for a small rotation. Okay, now okay, so let me stop here today. It has been a little larger discussion. What we have done is we have started by proving Euler's theorem and realized that any rotation about a fixed point in the rigid body can be written in terms of the rotation about an axis, and then we found the relation between the angle of rotation by this fixed one axis with respect to the Euler angles, or the relation between the Euler angle and this single angle of rotation. So if I can represent now in terms of any three Euler angles, I can find out what that rotation angle is, just putting in this formula, single rotation angle is. And then we figured out in terms of such a rotation how a general radius vector changes. So when I say in terms of such a rotation, in terms of that rotation angle and that axis, and that was a finite rotation, and we wrote down the similar expression for an infinitesimal rotation, and there can be differential form in that, and we saw that readily we could define an infinitesimal rotation vector, which was not possible in the case of finite rotation, and that we saw here why it was possible a little more explicitly. So we looked at Euler's theorem and infinitesimal and finite and infinitesimal rotation today. Thank you for the class. Bye.